If too much theory, scary equations, and procrastination has been holding you back from getting started with deep learning, this video has you covered. Over the course of the next several videos, I'll walk through simple code examples, and by the end of each video, you'll have your very own neural network to play with. So let's get started. We'll be working on one of the fundamental problems in computer vision, image classification. Image classification is the task of assigning a label to an image. So if I show you a picture of a cat, you'd say it's a cat. And that's exactly what we want our neural network to do. We'll show it images and it will tell us what those images are based on the examples that it's seen before. Here's a quick roadmap of what we'll cover today. We'll code up a neural network in Pytorch. We'll train and validate the neural network on the CIFAR10 dataset. And we'll compare the network's performance to a baseline random guess for that dataset. First, let's get some imports out of the way. Outside of the usual suspects, I want to highlight three of the imports. Torch.nn and functional give us the basic building blocks. Torch Vision Transforms has computer vision functionalities we can use on our dataset, and in fact, we'll use Torch Vision to import our dataset in the first place. Torch.optim contains various optimization algorithms we can use. So let's talk about the dataset now. We'll be working with the CIFAR10 dataset. This has images from 10 object categories, and hence the 10 in the name. And there are 50,000 training images and 10,000 test images. In this example, we'll not apply any fancy data transformations. All we want to do is normalize the images so that our neural network treats them well, and then convert them to tensors so that they can be passed through the neural network. Let's look at a couple of images to check if we've loaded them correctly. That seems to look fine. It's always good to start with a simple baseline to make sure everything is working properly. We can always increase the complexity over time. Our neural network will be a fully connected network. That just means it has a bunch of dense layers that are connected to each other. To feed this network images, we need to flatten images down to vectors. Our network has two layers excluding the output. The last layer has as many neurons as the number of classes in our dataset. The next step is to define the flow of data through the network. First, we flatten the image into a vector. This line simply makes the shape of the input change from this to this. After this step, we simply pass the data through the network, and between every two layers, add an activation function. The activation function is a way to add in non-linearity into the mix. Without these activations, our neural network will not be able to model complex relationships. We'll use the ReLU or rectified linear unit activation here. Let's initialize our model now. Oops, I forgot to call the parent class's constructor. Now it seems to be working. Now that we have our network defined, let's define our loss function and optimizer. We'll use the cross-entropy loss function, which is used for classification problems, and the SGD optimizer. The training step simply cycles through the data, shows them to the model, gets the predictions, computes the loss and the metrics, and finally backpropagates the gradients and updates the weights. At the end, we return the average loss and accuracy. An important note here is that accuracy isn't always the best metric to evaluate a model, but for this problem, it's sufficient. The validation step is very similar to the training step, except we don't need to update the model's weights, and therefore we don't need an optimizer. Training the neural network is simply about calling the train and validation steps one after another, and that's what we'll do here. Finally, let's look at the training curves to see how our simple model has done. A quick question for all of you. What is the bare minimum score a model needs to beat? In this case, it turns out to be 10%. Why? We have 10 classes, so a random guess is going to get it right in about 1 out of 10 times. That's about 10% accuracy. Does that make sense? Our model got about 40% after 20 epochs of training. The state-of-the-art ones score well over 90% on this dataset, so we have some work to do. We'll look at improving this model over the next series of videos. That's a wrap on training a simple neural network in Pytorch. If you enjoyed this video, you might enjoy this other one that I made. Until next time, happy learning!